Hello everyone. In this video we're going to be talking about linear approximation and differentials. So imagine that you're plotting a curve with a graphic utility. It might be Desmos or a calculator, and now you're going to pick a particular point on the curve and you're going to draw a tangent line in the curve and zoom on it several times. So something like this will be what happens. So you have the function here and you have this point and you have a tangent line there. Now you zoom on it in this curve. Now you're going to get closer, and when you get closer, this is pretty much the image you will see. If you get closer to that point, this is the image that you will see. So notice that as you get closer and closer to the point, the curve looks more like the tangent line. So the tangent line is a pretty good approximation of the value of what the function is. And this idea is going to be super important for the notion of linear approximation, which is essentially, well, if we want to approximate a value of a function in a point, we could potentially use the tangent line to create that approximation. So how do we use that tangent line? Well, if you remember, essentially the tangent line or a line in general is just given by a point and their slope. But as we know from the derivative, the tangent line of a point A equal f of A is given by this equation here, which is essentially f of A, which is the point, just at this point. And besides that, we're going to have the derivative in that point, which represents the slope. So f prime of A, the derivative of this point, represents the slope of the tangent line. And then we multiply by x minus A because we are making a line just at this point. So as you can see, this is the equation of the line, the tangent line at this point. And according to what we just mentioned, then we can just use this linear approximation to approximate the value around A. Okay? So in general, we need certain conditions to create this linear approximation. We need to assume that the function f is differentiable in the interval that contains the point A that you want. And the linear approximation is given by the function L of x, right? Which is going to be equals to f of A plus f prime of A, x minus A, for any x that is close to the point A. Okay, an interval I containing the point A that is super close to A. Now let's see an example of how we can use this into play. Now let's find first the linear approximation to f of x equals the square root of x equals 1, and use it to approximate a square root of 1.1. And then later, let's see what happens if we do the approximation at 0.1. So first, we construct the linear approximation. So we have this definition, and for the definition, we need to find out who is A. Of course, because x is equals 1, then we're going to call that A is 1. And if we have f of x being the square root of x, then f prime of x is just going to be 1 over 2 square root of x. And of course, we can plug at 1 and find out what is f of 1 and what is f prime of 1. Turns out that f of A, or f of 1 in this case, is just 1. Square root of 1 is 1. And now if I do f prime of A, or f prime of 1, turns out that that's going to be just 1/2. Now, if I plug these values on the equation here, then I'm going to get that L of x is 1 plus 1/2 x minus 1. And simplifying that, I'm going to get that this linear approximation is 1/2 x plus 1. Now, that's just the linear approximation, but how can we use that to approximate the square root of 1.1? Well, notice that 1.1 is a value that is super close to 1. So because it's super close to 1, we can do an approximation via the tangent line. So what we're going to do is we're going to plug 1.1 in the linear approximation, and that's going to approximate the value of the square root of 1.1. Actually, in this case, L of 1.1 is just going to be 1.05. And if we really take the calculator and we check what is the square root of 1.1, you're going to find out that that's 1.0488. So these two values are super close. So the approximation is really good. But normally then, because we're not using the calculator, then this is going to be a good approximation of our function at that point. Now, the exact value of f of 1.1, the square root of 1.1, is off by a little bit of 0.012. So it's a very small error. And in this case, our approximation is an over approximation, because notice that the tangent line is above the function. So if the tangent line is above the function, we're over approximating. We're getting a value that is bigger than the value of the function really is. Now, this is a table that describes some numbers that are very close. So for example, if we take x being 1.2, 1.1, 1.01, 1.01, 1.001, then we can see how much the approximation is going to be versus the actual value of the square root of x. So notice that this one, when it's 1.1, the exact value is 1.09, and the error was 4.6 times 10 to the minus 3, which is small, but it was considerable. But the more closer that we get to 1, the smaller the error is going to be. So you can see here the difference between the two values, the L of x and the exact square root of x that we get with the calculator. And at the end, when we're super close to 1, you can see that the error is so small that it doesn't really matter. So this is a pretty good approximation. Now, if we are going to find, let's say, the approximation to another function, like sine of x at x equals 0, and then use that to approximate sine of 2.5, I have a typo here, then what is going to happen is as follows. So we're going to have the function sine of x, which is given by the black line, and then we're going to get the linear approximation here, the line, which in this case is going to be x, by the way. You're going to see that in a minute. And this is an approximation that is difficult to see here if we're on top or we're on the bottom at the 0 point. So we'll check that in a second. Now, the graph of the function is a linear approximation at the point f of a, in case that it has that is common below, is doing an under approximation. So when we had the case that it was above, it was an over approximation. So we were given a higher value that the actual value is. But when we're below, like in this scenario, then we're doing an under approximation. And the value that you get from the tangent line is going to be smaller than the value of the function. Okay? This is going to have a relationship with the concavity of the function. So if f is concave up, the graph of the tangent line lies below, and you're going to do an under approximation. In the contrasting case, if you have the tangent line above, then the function is concave down, or if it's concave down, then the linear approximation is going to be on top, and it's going to be overestimating the values near a. Now, if we get the linear approximation to a function, let's say x to the 1/3, and we want to check at two different values. Let's check it at x equals 1 and at x equals 27. Now, we're going to use the linear approximation that we're going to get in this part to approximate 2 points. 2 to the 1/3, that is close to 1, and 26 to the 1/3, which is close to 27. Now, we want to know if these approximations are going to be overestimate or underestimate, and check the error for each of these parts. Okay, so let's see what happens here. So first, let's remember this is x to the 1/3. So when I calculate the derivative, is 1 over 3x to the 2/3. And then I can compute what is f of 1, what is f of 27, and I can compute f prime of 1 and f prime of 27. And in this particular cases, f of 1 is 1, f of 27 is 3, f prime of 1 is 1/3, f prime of 27 is 1 over 27. Notice that I'm talking about two different linear approximations, the approximation at 1, the approximation at 27. So that's going to give me two entire different linear approximations. So for the first one, f of 1 is 1, so I have f of 1. F prime of 1 is 1 over 3. So my first approximation is 1 plus 1/3 times x minus 1. That simplify is going to give me this line over here. And in the case when it's at 27, then I have that L2 of x is going to be 3, which is f of 27, plus 1 over 27, which is f prime of 27, x minus 27. So that's the second linear approximation, close to x equals 27. So now that I have the linear approximation both close to 1 and close to 27, then I can find out all the results that we want. So here, notice that this is x to the 1/3, so this is like cube root, right? And I can do cube root of 2, which is going to be like linear approximation in 2. And I just plug 2 in here. If I plug 2 in here, this is essentially 1 plus 2/3, right? 1 plus 1 over 3. And so this essentially is going to be like having 4/3, right? 1 is 3 over 3, and plus 1/3 is going to be 4 over 3. Okay? And so that will be the estimate that I get when I'm closer to 1 of L1 of 2, or cube root of 2. Now, if I want to do cube root of 26, cube root of 26 is closer to 27, so I can use this linear approximation here. And this is going to be 1 over 27 times 26 plus 2, and this is approximately 2.963. Now, in terms of approximation or under approximation or over approximation, we can see that for x equals 1 and x equals 27, we have concavity down on both of these points. So on both of these scenarios, we still have overestimates, where the tangent line is above the original functions, and we're going to get an overestimate. Now, if we calculate the difference between both the approximation and the actual value, then we can compute the errors. For example, L1 of 2 minus 2 to the 1/3 is going to have a real difference of 0.073. And if I do L2 of 26 minus 26 to the 1/3, which is the error around 26, is going to give me a very small number of 0.00047. Now, because f2 prime of 1 and f2 prime of 27 are very much small numbers, and the curvature of f is much greater at x equals 1 than at x equals 27. And so this just showcases why the approximation of a square root of cube root of 26 is going to be much more accurate than the approximation of cube root of 2. As you can notice, this has a much smaller error than this one. Now, when we're talking about differentials, we can talk about the relationship between the change in x and the change in y. So remember that if f is a differentiable function on an interval I that contains a point, the change in the value between the 2 points a and a plus delta x is going to be approximately the delta y in terms of f prime of a and delta x, in the way that delta y is approximately f prime of a times delta x. And you can see this also as well as the change in y over the change in x is going to be the approximation to f prime of a when we're in an interval close to a. And so thanks to that, we can think of the uses of linear approximation. We can use this L of x operator here to approximate near a value of x equals a. And we can use the formula for the delta to approximate the change in y on the dependent variable when the independent variable is changing. So it all depends on how much information you have. If you have information in the change versus if you have information on the function. Now, in terms of differential, if f is a differentiable on an interval containing x, a small change in x is denoted by the differential delta x. And the corresponding change on f is approximated by the differential in y. So that's why we have the relationship a differential in y is equals to f prime of x differential in x. And you will not be surprised by this, because another way of just mentioning the y dx is f prime of x. So this is another notation for this. Now let's see an example of this in terms of applications, or an example. We're going to use the notation of differential to write an approximate change in the function 3 cosine square of x, given that we're making a small change in the x. So if f of x is 3 cosine of square, then we're going to have that f prime is going to be minus 6 cosine of x sine of x. Or simplifying that, we can see this as minus 3 sine of 2x with double angle identities. So this means that dy is f prime of x dx, which will be minus 3 sine of 2x dx. Now, thanks to that, the interpretation is that a small change in delta x is going to produce an approximate change in the dependent variable delta y equals minus 3 sine of 2x dx. And so, for example, if we're making a change from x equals pi over 4 to pi over 4 plus 1, then the delta is the change between these two. That will be 0.1, which is the difference in this. And the delta y will be just minus 3 sine of pi half times 0.1. And this will be equals to minus 0.3. Okay? And so this minus means that the approximate change in the function is minus 0.3, which means that it's going to decrease approximately 0.3. And so this is the end of the introduction to linear approximation and differentials. So make sure to take a look at the practice videos.